Hello everyone, I'm happy to welcome you to the A4Q World Congress. Today I have Tilo Linz, the CEO of the imbus AG here, and he will present today at the A4Q World Congress. Thank you for being here, and now I'm happy to hand over to you.
Thank you, Jelena. Very many thanks for your friendly introduction of myself. And I'm very pleased to have been invited to speak here for the next couple of minutes to you at this A4Q World Conference. And I like to share the topic, how to test autonomous systems, with you in the following minutes. So let me see if I can manage him a system. Oh. So what I like to present is my experience and the imbus company experience about testing such kind of systems. We are active in the software testing field since about nearly 30 years now, and all of our customers where we have been able to assist them in software testing, of course, have always presented us and confronted us with the most modern and innovative systems at their time. And so it's clear that today we are also asked more often every day to assist perhaps in the field of testing autonomous driving functions or robot related functions and so on. And so we are interested in improving our practice and doing and testing which kind of systems. And I like to share a little bit about that with you during the next speech. And first of all, I will discuss some characteristics of autonomous systems to make clear what I understand with that term. Then I will give you some overview of the basics of testing there and what is different to testing traditional systems. Then I will highlight from my point of view, most important technique or approach in testing, which is called scenario-based testing. And then I like to give you a little outlook what might happen in the future. So first, let's have a look on what kind of systems I'm talking about. There are a couple of definitions out there about such kind of systems. And if you are thinking about what are autonomous systems, which of course this thinking will start or can start with talking and thinking about systems which are just not with a pilot or with a driver on board. Maybe originally this term unmanned systems has meant systems which are just remote controlled. And there's a definition from the National Institute of Standardization from the US from 2008, which is about unmanned systems. And an unmanned system is a powered physical system with no human operator aboard and the principal components which acts in the physical world to accomplish assigned tasks. And it may be mobile or stationary. And today's definition is from the latest draft version of ISO 8373 from 2020. It's just under development. And this term here is in the ISO norm defining what is autonomy of a robot, and autonomous robot thus is a robot which has the ability to perform intended tasks based on current state and sensing without human intervention. And so we have now a definition for remote control system or more advanced system, which is completely autonomous, an autonomous robot. And what you might also have, should have in mind are things which are perhaps much smaller, little things like perhaps insects, which are in the near future or in 10 years flying around us. So that is the third definition of autonomous things, which can be an information source that has the intelligence to operate autonomously and to communicate, collaborate when appropriate or necessary, and act on its own. Some of the things will be fixed or stationary, and some will be mobile. So an autonomous thing from this definition could also be virtual, just a piece of software anywhere in the internet. What I'm talking about in this speech is the autonomous systems following this more general definition: a vehicle, robot, or device which is capable of self-controlled movement within its operational domain to accomplish intended missions without human intervention. So what my talk now is about is autonomous systems which share these three important characteristics. That is, they are cyber-physical. That means they are built from a combination of software pieces together with electronics and mechanical components. They are mobile, which means that such systems can move around, that can navigate around, self-controlled without necessarily a driver or pilot is on board. And also very, very important, the systems always are dedicated to a mission which they are designed for. So they are built to be able to accomplish a certain kind of mission, for example, as a service robot to help its users to do something in a household or in a kitchen or in a hospital or something like that. Of course, if you're looking at these systems today, the technology is not yet such advanced that all these systems are fully autonomous. But what we are seeing today is that these systems are evolving. They are today in need of cooperation with the user, and often or mainly the user has to control them, has to guide them, has to remote control them. But the process is ongoing that these kind of systems are getting more intelligent each day. And so parts of this talk, of course, are about what we as software testers will be confronted with in the future. Well, one term which I have mentioned already sometimes is the term autonomy. So let's have a look on what autonomy is meaning, and is also to be found in the National Institute standard from 2008. So an unmanned system or an autonomous system owns the ability of integrated sensing, perceiving, analyzing, communicating, planning, decision-making, and acting or executing something to achieve its goal as assigned by its human operator. So that is always the definition of what autonomy is talking about. So it's a kind of what the system and is able to sense and perceive from its environment. We'll have a little bit more closer look on that. And if you are thinking about whether a system is driving across the world on its own, so it's more or less clear that the system has to have some abilities to understand and to perceive its environment, and these abilities must continuously be processed by the system. So an autonomous acting system must be able to continuously perform these three tasks in an ongoing circle or in parallel. It must be able to sense its current environment, capture the signals from its sensors occurring in this environment, and it must be perhaps able to recognize pattern already on the sensor level. When having done that, the system must be able to understand what the sensors are telling it. It must be able to plan and select actions, appropriate one or best actions to respond on its current situation. And then, of course, not only to the current situation, but also to the mission which should be achieved at the end of the mission. And this is called the planning phase. And when of course, the system has to run, if it has planned something, it has to act by triggering and controlling the selected action to make this plan happen. For example, to switch on a motor to move forward, or to brake because there's an obstacle has been detected by the sensors, and so on. And this process is called in the area of robotics, the SPA cycle. In the area of autonomous driving, it's called the OEDR cycle. And sometimes in advertisement, you can also read that the people are talking about the sense, think, and act cycle. So, of course, the way the system is working here highly is interrelated with its intelligence. So if it has weak sense, plan, act cycle, it has lower intelligence. If it is more sophisticated, it has higher intelligence and higher abilities to move around in its environment. And why I'm telling all that, because of course my topic is how to test such systems. And if you are trying to figure out how to test such systems, you have to first understand what the core functionality of a system is, and how the system in general works, to be able to start thinking about how to test it. And that is my second chapter here. If you're thinking about what you have to test or what you shall test, then you have to think about autonomy of a system. And that is, of course, the SPA cycle I just mentioned. So as I told, if the SPA cycle is advanced, when the system has the ability to navigate in complex environments, if the SPA cycle or the sensors and the understanding and processing of the sensor signals is weak, when it can only navigate in a simple environment. And that means that the dimension of autonomy, where the system is moving around, are heavily interrelated with the things you have to test, because as always in testing is about covering some things. In traditional testing, it's about covering the functionality. In testing autonomous system, it's about covering the functionality plus functionality in all these dimensions. And also, these dimensions are well defined in a formal framework from the NIST, the autonomy levels for unmanned systems framework, where following this framework you can measure and measure the degree of autonomy the system has to act in. And of course, if you are experienced testers already, you are aware that testing is always about testing all combinations of something and all the possible intended combinations, but also the impossible, unexpected combinations. And that's also here the case. So if you are thinking how much effort do you have to spend testing such an autonomous system, which test cases you need, which environment you need, which mission should be part of your test plan. You have to think about in what environment the system shall or is intended to move, what kind of missions should the systems can achieve, what kind and degree of human interaction is necessary in which situation. And when you are trying to put test cases in your test plan which cover many different, or as much as possible, as many as possible different points in this space of possibilities. And also, don't forget, also here, of course, it's also about testing at the borders of the space. So you and behind, of course, you also always should put in test cases and execute test cases where you put the systems in an environment where it's not intended to be there, and to check how the systems will behave. For example, let me give you a short example. No, here. Okay, I hope you can see that. That is, of course, such a situation from the editorial from Boston Dynamics about their robot, where the system has encountered a situation which was perhaps not intended. But the system recovered and goes on its mission, and that could be, of course, when a testing task to let the system navigate in an unexpected situation, and then watch the system, how the system recovers from this unintended situation. And then, of course, you can decide, is that recovering of a system a good strategy, or did the system fail to recover? And that is when the outcome of the test, and you can say, okay, the test passed or the test failed. But the general functionality of the systems was in that situation not the point you were testing for. You have been in this situation, you are testing for how the functionality which the system can perform is performed in this certain situation and environment. And that is something that is different to traditional testing from my point of view, that the environment where you are executing the test case has so heavy impact on whether the system can realize its function. And that, of course, means that with dimensions of autonomy dramatically increase the test effort, of course, because you not only have to test certain functions in a certain specific environment, so you have to test all these possible functions in all possible points in the world where you put in your system. And that means that the complexity of testing and the effort of testing and the amount of test cases needed dramatically explodes. And now back to the functionality point. So if you have seen now several completely different kinds of autonomous systems, for example, self-driving cars, self-walking robots, flying drones, you can expect that testing them is completely different. No, that's not the case. So if you are thinking about what to test according such systems, then it's a good strategy to have a look into the ISO 25010, which lists the top-level topics you shall consider making your test plan. Of course, that is functional suitability, which is performance efficiency, it's reliability, it's security, usability, maintainability, portability, and compatibility. And starting with this list is always a good idea to then think about for each topic, what does that mean with this functionality, for example, to drive forward? What does that mean for this system in these dimensions? And then you have to analyze for each chapter of this list, what does that mean in your context for your special system? And then you can derive your test plan according to ISO 25010. To give you some examples, performance efficiency. So in traditional systems, performance means how fast the system reacts to the user input. In the context of testing a robot, for example, it might mean that the time behavior of the system and its components and consumption of resources must be checked. That may be a possible question which you can cover by a test case or a set of test cases. You exercise a function, for example, whether the system can detect an obstacle, or you can send your system to a mission, for example, to a robot. You can say, okay, drive in the kitchen room and pick up a glass and bring it back to me filled with water. And then maybe there's a performance requirement, which means that the time the robot needs to grab a glass of water is below 10 seconds or below 1 second or below 20 seconds. So that is our typical performance efficiency requirements, which could be tested. Or another one is that the movement of the system shall be in range between some minimum or maximum speed, and so on. And one interesting thing here is also to check resource consumption. For example, especially battery power management. So run the longest application scenario, you are aware, and check the battery power management, or start the mission on low battery power and check how the systems behaves, and so on. So that are, of course, a lot of things which are hardware influenced, which you have to keep in mind and put as part of your test plan on the test plan. Another example is about security of the system. And security shall check how resistant the system is against unwanted access or criminal attack on data of the system or on data of its user or on the entire system itself. And questions you shall ask can be, for example, does the operator need a password to switch the system on, and is that secure enough? And that is important because if you have a service robot and maybe the service robot is to a certain degree autonomous, then of course there are many systems where you have to control it by touchscreen or by Wi-Fi or by Bluetooth from your mobile phone. And of course, in such situations, when you are controlling the robot by Wi-Fi, it could be the case that if this communication is insecure, about an insecure channel, then your neighbor or some other attacker can take over the system, and then it's not longer your system. And if the system is able to grab something, then of course the robot can grab you instead of your glass of water. And so security is really challenging and an important topic in testing such systems, because in worst cases, the system can change from a system which is built to help you, to assist you, into a weapon, just because it's attacked and overtaken by an attacker. And so checking for security is always self-relevant and is always involved with checking for safety of the system. And that is the next important point. Testing such systems always is highly interwoven with testing the safety of the system. That because of, it might be clear, the functionality of the system, to build such a system which can do all these things on a functional level, is difficult but achievable. But to make it safe, that is really hard. And such systems, for example, a self-driving car, have 2,000 kilograms in mass, and if driving with 100 kilometers per hour, for example, and that is of course a very dangerous safety relevant thing if it's moving around uncontrolled. And what can happen here? Of course, the system can infringe uninvolved third parties, passengers around the street. It can violate the users, the operators, and the passengers of itself. It can injure animals, things, and objects which are getting into its track. It can damage other objects. Perhaps the robot, which is grabbing a glass of water, can destroy the glass or the rest of the kitchen, whatever. And it can, of course, damage itself if it's maneuvering in a completely out of control way. It can damage itself. And all of these things are, of course, things which are likely to be tested. And one last thing on testing for safety. Maybe if you are already working in the automotive industry, you are aware of that. Safe testing for safety means the system shall be safe during its normal operational state. If everything is running well, the system shall behave safe. And it shall then also be safe if something is malfunctioning. And that is the classical view on safety. If the system has an error, a hardware error, then it should be stopped. It should stop and enter a safe state. Here in testing autonomous systems, which things are a little bit more complicated, because if you're thinking about a car, self-driving car is driving on the highway with 150 miles per hour, for example, or in Germany at least. And when a sensor is malfunctioning and the system gets aware of a failing sensor and decides to stop immediately because it has to enter a safe state, standing still on the highway is not a very good idea. So the system, in reality, the self-driving car shall indeed having censored a malfunction, not stop, but lowering the speed, driving to the right line, stopping near the street or besides the street, and then calling via internet perhaps a breakdown service. So that is completely different to traditional today's system, who just stop working in a failure mode situation. And that is the difference between failing safe versus failing operational. Yes, and that means safety, testing for safety is a very, very important part of your test plan. But the bad news is that is not an isolated topic as one chapter inside your test plan. It's distributed across all chapters, and for every chapter you have to consider what safety relevant questions you have to answer as tester. Okay. So we have now discussed all the basics about how testing, what is an autonomous system, how testing in general on a high level is different from testing traditional IT systems. And now I like to highlight some aspects of what is the practical approach to test some such systems. And the most important practical approach from our experience is the so-called scenario-based testing method. Yes, what are scenarios? Scenarios, for example, imagine a robot you have to test, or a self-driving car passes its test in one environment, for example, on a parking lot, and in a few other environments, for example, on a small street where nobody else is driving around. When normally as tester, you would say, okay, the system has passed its test. In this case, the system may still be totally unsuitable for operation in the real world, and it even may pose an extreme safety risk, as I explained already. So therefore, during testing, you not only have to create variants in the functionality tests or in the functionality related tests, you have to create variants in also along the dimensions of autonomy, environmental complexity, mission complexity, and in the degree of human interaction. And that is what I already explained during the last minutes about these dimensions and about what is critical in testing autonomous systems. But what we are needing here in practice is we need a formal approach to model these variations, so that we can systematically figure out whether there are situations we have not covered and whether there are situations we don't need to cover. So not only by guessing that, but by really figuring that out by following a systematic approach. And here in the solution here is working with formally defined scenarios. So what is a scenario? So there's also a standard, and a currently evolving standard from SM, the SM Open Scenario Standard. And SM is a standard organization which is mainly active in the automotive industry, and which is a forum for discussing between experts from automotive industry, from research institutes, about standardizing the ways how automotive tests, and especially in the area of simulation, are to be performed. And this standard also defines the topic scenario, and the scenario here is a specific description of how the view of the world or the scene changes with time or over time, usually from a specific perspective in the context of vehicles and driving. This will encompass the developing view of both world fixed elements, such as, for example, road layouts and static furniture, and world-changing elements such as weather, lighting, dynamically moving elements such as other vehicles, objects, people, or animals. So scenario means a formally described piece of the world with buildings, with streets, with cars, with passengers, and some rules how these objects are moving around. So, and scenario-based testing then is testing the behavior of a test object, and this test object can be a complete system or a component or a function of the system within one of these formally defined scenarios by executing the scenario via simulation or in the real world. So the term scenario-based testing, that is important, is not limited to testing in a simulated world. It is also possible, and it's also done, to use that to test the system in a real world or in a hybrid approach. Some parts of the system in a real world, other parts of the systems only simulated. And to make things clearer, so that what I show you here is the way such scenarios perhaps can be formulated in the future, because that is here example taken from SM Open Scenario version 2, which is currently under discussion. And the current version 1 is much more easier. The current version 1 is XML format for defining such a scenario in coordinate system-like way. So you are on a much more simpler level than in version 1. And the challenge for version 2 and the need is to find a level of abstraction where you can define such a scenario on a more high-level view, in a more abstract way. And that is an example which perhaps next year might look like. So you can here define the cars which are moving around, and you can define how they should navigate. And for example, here you can define drive 1 starts at this position behind car 2, and when the car shall overtake the car in front of it, and the end of the scenario, at the end of the scenario, the car 1 should be ahead of car 2. So, which is just a description of what should happen, and not the description about how the autonomous system shall achieve this. So that is exactly what we need for testing autonomous systems. So the test case is not like in traditional testing, do that and that and that and that, and then you must be there. The test case is just to state a mission. Well, you are here, here's your starting point, and you shall be there in 10 minutes. And then the rest in between is up to you, to your system. Maybe you define some constraints that your system should maneuver behind in an interval of a certain speed or something like that. But the details of how the system acts is up to the system, because the system is autonomous or shall be autonomous and manage that. And here, visualized in a two-dimensional way, you can see this scenario says, okay, this red car is our test object, and this sensors of that car shall be aware that there's a car in front, and then this car on its own shall decide whether to overtake or not. And if overtaking, of course, that should be safe. And in the end, the car should have done a good overtake maneuver. And the rest of the scenario is static, which are some streets, some roads, and maybe some houses and other objects. And what you shall be aware in this situation is that the simulation system is controlling the yellow objects. These objects are completely under control of the simulation and are only doing what the simulation likes to have them done. But the test object itself, the red car, this is containing the software under test, or the hardware under test, the software under test, the components under test. So, for example, if you are testing here such an function which is or should be capable of managing overtake maneuvers, when this function is not part of the simulator, this function is part of or is delivered by your software developers who have the job to build this function. And when it's injected in the simulated object here, in this so-called ego car. And the general architecture of testing here, of test automation, is similar to that what we see today in testing and automated testing of normal systems. You have a test management system, for example, some of the imbus test management systems. These systems are managing the test cases within a test repository, but you also have a repository of all these scenarios which are describing the certain kinds of worlds where your systems have to move in. And you have then also some kind of scenario management where you can say, perhaps, well, give me all the scenarios on highways, or give me all scenarios with an intersection, or give me scenarios with more than 20 cars driving around, and so on. So you like to have the ability to select certain scenarios, combine them with the test cases of functionality of the system, and then, of course, you select a couple of scenarios to be executed, deploy them to the test automation layer, which is the simulation environment, or maybe also equipment in a real-world car driving in a test space. And then this simulation interacts with your test object. The simulation is run. The simulation is collecting all the sensor data and data generated during the simulation. And if the simulation finished, then the data is uploaded back to the test management. And in the test management, there is, of course, then noticed whether the test or with several sections within the simulation which you declare as test relevant have been passed or failed, and so on. And to make that with a second example a little bit more understandable, here this is a turn right scenario at the next intersection. So we have, it's now 3 cars, the ego car, the car number 3 here again, and the mission is that the car, the test object has to turn right at the next intersection. So the test case, of course, then is, does the ego car turn right? Does it sense? It's sensing. Does it be aware that there is an intersection? And second, when if in turning right, is the system keeping the right lane, or is it driving somewhere? And of course, you have in the world of simulators also the possibility to do simulations which are visualized by 3-dimensional visualization. I have here a small artificial example It's not from a real world test scenario. It's just collected here for my speech to make it a little bit more understandable what's going on. And remember the test automation architecture. The test manager here has selected a test case, turn right at intersection. And when this test scenario is deployed to this simulator, which is here the so-called Kala simulator, which is an open source system. And that here, the black car is our test object. And car 1 and 2 are starting, and our test object here is now going right because there's an intersection and, well, not really keeping the right lane because through any mole function whatsoever. And so that would be an example of a failed test case. And as you have seen, whether the test case fails or not depends on where in the scenario, at which point in time the test object is at which place, and whether you have specified whether this place or this speed or this mass or whatever is within the constraint you have defining your test case. And if you are doing this kind of tests, of course, at different corners, at different intersections with different cars in front and behind, in different daylight, at nighttime, at raining, when it's raining and so on, you can rerun always the same mission, turn right at the next intersection, but in completely different environments. And if a test object fails in this situation, it might pass in another situation. And so it's really about covering interesting or less interesting or risky or less risky situations. So that have been the ideas and concepts and general concepts I'd like to explain a little bit about, to give you an impression about what is meant by testing autonomous systems. So it's a wide range, a wide field from testing autonomous cars or self-driving cars on a different levels, from the current today's level 3 systems to tomorrow's level SAE level 4 systems, or sometimes in the next years to level 5 systems. It can be meaning and involving testing autonomous robots or drones, or also equipment which is driving in water, undersea, or on the sea. I don't know what kind of systems will be confronted over the next years, but to summarize, testing such systems always is meaning that you have to test along this sense, plan, act cycle. So you have to test whether sensing is doing what it should. You have to test whether the planning and the understanding of a system, of its mission and surrounding is as expected. And you have to test whether the system, if it's acting in the way that is expected. And finding test topics is easy because you just can consult the ISO 25010. You additionally always have to be aware that testing for safety is a really important thing. And you have to be aware, of course, that the test space is dramatically higher than all these huge test spaces we are confronted as testers every day. And you have to really be careful which point in this test space you pick as environment for which mission where you are trying to test whether the system can accomplish this mission. And of course, repeating the same test in all these, or a couple or a huge couple of different selected points in this space is essential, and that is the success factor. And of course, you have to repeat such an enormous amount of test cases. Most of these things have to be done in virtual simulated worlds because it's too expensive, has too much effort involved if you try to test all that in real life. And the state-of-the-art approach for such testing is scenario-based testing. And the last idea, so my closing idea, if you are thinking about autonomy and intelligence, that of course, I think it's clear that a fully autonomous system, which should be able to accomplish a certain mission goal without human interaction, for example, a service robot, which you can say, please go to the kitchen and get me a bottle of water, must be able to recognize, interpret, and understand its situation in a certain way within the area where the system is operating. And of course, it must be able to decide upon appropriate actions regarding to its mission. And if you're thinking about that, it's clear that a system that can do something like that has a degree of intelligence which is similar to a degree of intelligence of human beings. And the question only is to which degree. And what I'm saying is intelligence of an autonomous systems is the degree to which the system can accomplish a set of certain missions of a certain complexity, MC, within an environment complexity of EC, having human independence of HI. And so you have a more formal definition of what intelligence is. And the consequence might be that in the near or wider future, software testers will measure what intelligence degree is realized by a system, and not anymore psychologists as today measuring or trying to measure human intelligence. And just by applying a reproducible scenario-based testing, because if you're doing that, you can formally describe the scenarios, you can formally measure the complexity of the scenarios, and you can measure how many of your test cases are passed. And as a result, you can calculate an index figure, which is mapping the intelligence of a system to a number. And that is nothing other than measuring intelligence quotient like today for human beings. And of course, maybe then you can compete as human being with the intelligence of such artificial autonomous systems. But that's not tomorrow. So thank you very much for listening. That was my last slide. If you are interested in the topic, here I have put into the slides a list of sources and further readings. All the standards I mentioned you can find there, and links to the Kala simulator, to the test bench, and any other literature which is have been mentioned in my speech. So thank you very much for listening. Are there any questions?
Thank you, Tilo, for joining us and for the interesting presentations. We did receive actually some comments in Facebook. Maybe we can answer them directly in Facebook because we were running out of time and we need to go like to the next presentation now. But there were like interested people in the presentation, and we did receive comments in different topics, and we will clarify after presentation that we will have them answered afterwards. So thank you, Tilo, for joining us.
Yes, thank you.